Example 1, limit as x approaches 0 of 1 minus cosine x over x. If we look at our numerator as x approaches 0 is going to 1 minus 1. So we see we have a 0 over, and as x approaches 0, that is a 0 over 0 case. So let's go ahead and apply L'Hopital's rule, the first form of that. All right, I'm just going to go ahead and say I'm using L'Hopital's rule. Keep my limit as x approaches 0. The derivative of 1 minus cosine x is sine x. And the derivative of x is 1. So now that we can evaluate this, the limit is then 0. And that's all there is to it. Make sure it actually applies, but then take the derivatives and then see if you can evaluate from there. We can actually use L'Hopital's rule more than once. We can apply it more than once in its stronger form, but we kind of want to avoid that if we can. And they will not always be so straightforward either. All right, so x approaches 1 of sine of pi x over ln x. Well, as x approaches 1, natural log goes to 0. I just noticed that. Now here, sine of pi is 0, so this is actually approaching 0 as well. Alright, so let's go ahead and use L'Hopital's rule. Limit as x approaches 1 of, and we'll take the derivative there, so that would be pi from our chain rule, cosine pi x over 1 over x. Now, let's evaluate again. So the denominator is going to, as you approach 1, that's going to 1. The numerator is going to, that would be negative 1 pi, so negative pi. And I'm going to go ahead and rewrite this. This is not L'Hopital's rule. I'm just simply rearranging pi x cosine of pi x. And if we evaluate that at 1, we do in fact get negative pi. Okay. And there's the website you can go to download the entire text. I would suggest you do that at some point. It's a pretty good book. Alright, example 3, evaluate. As x goes to infinity, e to the 1 over x minus 1 over 1 over x. Well, as x approaches infinity, we saw this with our end behavior section. As x approaches infinity, the denominator is actually going to 0. Denominator is going to 0. Our numerator, this is going to, this exponent is going to 0, so that is 1 minus 1, so this is also going to 0. Because L'Hopital's rule applies, go ahead and keep our limit. Now the derivative of the numerator is e to the 1 over x times negative 1 over x squared. And the derivative of our denominator is negative 1 over x squared. So algebraically, this is equivalent to the limit of e to the 1 over x. And as we noted earlier, that actually goes to 1. So our limit there is 1. Number 4, limit as x approaches 0 of sine x minus x over x squared. Well, the denominator is going to 0, and the numerator is going to 0 minus 0, so that is also going to 0. So we'll go ahead and apply L'Hopital's rule. That would be cosine x minus 1 over 2x. Now, investigate again. If you go to 0, the denominator is going to 0. The numerator is going to 0 as well. So we can still apply L'Hopital's rule. We'll go ahead and do that. Limit as x approaches 0. And the derivative there would be sine x over 2. Nope, negative sine x over 2. Evaluating that at 0 gives us 0. So our limit is 0 in that case. Number 5, this is something from end behavior actually of a rational function. Each of those, numerator and denominator, are both going to infinity. So if we take the limit, that would be 3 over 2, which is just 3 over 2. It's a constant. Because, again, this is an infinity over infinity case. That simplifies our end behavior questions quite a bit, if you recall. All right, limit as x approaches 0 from the positive, from the right side, of natural log x over cotangent x. Well, the numerator is going to negative infinity. The denominator is going to positive infinity. Doesn't matter that they're different directions, that it is an infinity over infinity case. So let's go ahead and apply L'Hopital's rule. X approaches 0 from the right. Be 1 over x divided by negative cosecant squared x. Which, if you think about going to 0, the numerator is infinity, the denominator is still infinity. I'm going to rearrange this algebraically. Again, I'm not applying L'Hopital's rule, I just want to rearrange it. That would be negative sine squared x over x. Well, because we know sine x over x goes to 1, that's just a given limit. Let's go ahead and write this. Sine x over x times negative sine x. This limit is 1, and this limit is 0. So our limit is 0. Looking at number 7. As x approaches 1, okay, well, the numerator is going to 6, and the denominator is going to 7. L'Hopital's rule does not apply. L'Hopital's rule does not apply here. If we, in fact, did apply L'Hopital's rule, okay, well, in this case, the limit is exactly 6/7, because we can evaluate in this one. There is no discontinuity, nothing's going to infinity or 0, so it's just 6/7. If you did, however, apply L'Hopital's rule incorrectly here, that would be 2x over 3, and that limit is 2/3, which, again, is not true. So we can't apply L'Hopital's rule there. Can we apply L'Hopital's rule to limit the limit as x approaches 0 from the right of cosine x over x? Well, if we evaluate at 0, or we see where that limit's going, this is going to 0, and this is going to 1. So this is a 1 over infinity. So no, we cannot apply L'Hopital's rule here. In fact, the limit here is going to be infinity, because it's going to 1 over 0. But the answer to the question, no. L'Hopital's rule does not apply. You have to have limits of a certain form. 0 over 0, infinity over infinity. Okay. So this limit is going to 0, and this is going to infinity, which is why I have written here the 0 times infinity. This is a separate case. Okay. So this does not work out very nicely. It does not fit into L'Hopital's rule. However, if we can write this as a quotient, if we could write this as a quotient that is going to 0 over 0 or infinity over infinity, then we can apply L'Hopital's rule. The easiest way to do this is natural log of x over 1 over x. Because they are 0 and infinity, we can actually flip over the x, and that is going to then go to infinity. All right, so we have infinity over infinity at this point. So let's apply L'Hopital's rule. The derivative of Natural log is 1 over x. Derivative of 1 over x is negative 1 over x squared. Rearranging this, that is going to be negative x, and so that limit is in fact 0. Number 9. This one's going to be an infinity minus infinity case. So the limit as x approaches 0 is 1 over x squared minus 1 over tan x. Well, 1 over tangent is going to go to infinity as x approaches 0, because this is going to 0, so then this is going to infinity. Same thing here. This is going to infinity. So let's first see if we can algebraically manipulate this. If we got a common denominator, this would be tangent x minus x squared over x squared tangent x. Which, if we examine this, this is going to 0 over 0. So L'Hopital's rule now applies. Okay, we approach 0 from the right. Let's go ahead and take the derivative. So the derivative of tangent is secant squared x minus 2x for the x squared. And the product rule will give us x squared secant squared x plus 2x tan x. Okay, now secant squared is going to 1. 2x is going to 0. Because x goes to 0, or x squared goes to 0. And then this term goes to 0 as well. So it appears this limit is now a 1 over 0, which means the limit is positive infinity. Because x is coming from the right, it's going to be a positive infinity. Go ahead and add that note in there. All right, number 10. Again, this one is going to be as x goes to infinity, and infinity over 0. So we have to use a slightly different tactic here. Let's go ahead and we're going to use logarithmic properties here. So I'm going to go ahead and take, so this limit is going to be the same. Well, actually, let's not say that. Let's consider natural log of limit as x approaches infinity of x to the 1 over x. That is the same limit as the limit as x approaches infinity of 1 of natural log of x to the 1 over x, which is then equivalent to, we're going to come back to our original question eventually, 1 over x, okay, 1 over x ln x, or times ln x. So I'm going to go ahead and write that as ln x over x. Now, as x approaches infinity, this is going to an infinity over infinity case. So if we apply L'Hopital's rule at this point, the limit as x approaches infinity of 1 over x over 1, and that limit is going to be 0. Now, since the limit, or add this in here, since the natural log of the limit as x approaches infinity of x 1 over x, let's go ahead and change that. Since that limit equals 0, the limit as x approaches infinity of x 1 over x equals e to the 0, or 1. So our limit is actually 1 in this case. Now, because we have that 1 over x as an exponent, that's where that comes in handy. So let's actually use the same idea for the second one. This one's going to be a 0 to the 0. So L'Hopital's rule does not apply, so we need to rearrange it algebraically to get it in that form, 0 over 0, infinity over infinity. All right, well, applying our natural log properties, Okay, if we take the natural log of this, that is going to be the limit as x approaches 0 from the right, sine x times ln x. Now that is a 0 times infinity. So we'll kind of pull the same trick we did earlier algebraically and make this natural log x over cosecant x. We did this before, but it was with an x. We made it a 1 over x. Okay, now this is in the form infinity over infinity. All right, applying L'Hopital's rule here, that is the limit as x approaches 0 from the right of 1 over x over negative cosecant x cotangent x. Let's go ahead and rearrange that. Okay, to be, put the x in the denominator and flip the rest of this. So we'll have a negative sine x tan x. Actually, I'm just going to leave it written like that, because we know that as we approach 0, this expression goes to 1 and this goes to 0. So the limit of the natural log of our original problem is 0. Okay, so again, since the natural log of that limit equals 0, the original limit is going to be 1, which is e to the 0. So that limit is 1.